Mission fueled by passion, a remarkable spark of engineering brilliance and astronomical ambitions, Chandrayaan 3 inspires millions of us for its historic feat to land on the moon's surface on 23rd August 2023. This milestone has been important for India in securing an elite fourth position after America, Russia, and China to have its spacecraft soft landed on the moon. Chandrayaan 3 also holds significance as the second moon craft to have landed on the South Pole after China, also considered as one of the moon's toughest terrains. This project was launched by the Indian Space Research Organization to understand more about the moon's composition, its geology, minerals, and so on. For this, Chandrayaan 3 carries advanced technologies like RF altimeters and propulsion systems. Let us know more about this by the experts involved in designing the instrumentations of such spacecrafts and contributing to similar such mega missions. Today we have with us Professor Bhas Bapat, who is the Professor of Physics and former Dean of Academics at IISER Pune. He has also held position as the Dean of Academics at IISER Tirupati and has been associated as a faculty member at the Physical Research Laboratory since 2001. Professor Bapat has his research interests in experimental physics involving atomic collisions and molecular fragmentations. His research group at PRL, Ahmedabad, is also involved in designing the solar wind and spectrometer for Aditya L1, which is India's first solar probe mission planned by the Indian Space Research Organization. I welcome you, sir, to the Science Activity Center at IISER Pune.
Right. So, Shweta, I'm sure you must have seen the moon several times, and like all of us, all of our ancestors, right from the point that humanity came into existence, must have been fascinated by the moon, which is the closest heavenly body to us, and you see it every night. So the fascination for it must have grown. But I think the major improvement in our understanding of what the sun is, what the moon is, must have actually happened when the telescope was first invented, and scientists and other lay people also started looking at the moon through the telescope, discovering its features, discovering what surface it has, and so on and so forth. But I think one of the major changes or major improvement of the understanding of the moon, I think we should say that it really took a great leap forward once we started sending missions to the moon. And the reason why I say this is that you must have heard this in your school books, and I think all of us know of this by now, that we are able to see only one side of the moon at all times. And the reason for this is simply that the moon spins at a certain rate, and the rate at which it revolves around the earth is also the same, or very nearly the same. And as a result of which, only one side of the moon is always visible to us. To be able to see the other side, we have to jump out of the earth or go away from the earth and look at the other side. And after a lot of observations, several decades or perhaps centuries of observations, there are many things that we know about the moon now. For instance, as I said, we know that the rate of revolution and rate of rotation is very nearly the same, and we also know that the Earth's gravitational pull is much stronger than that of the moon. Roughly 1/6 is what the moon has, and we also see phenomena like the lunar eclipse or the solar eclipse, which are both of them happen because of the moon.
Yes.
And the interesting thing is that the eclipses don't happen on every new moon or every full moon, and that also tells us that the orbits in which the moon goes around the earth and the orbit in which the earth goes around the sun are not quite coplanar, or they are not identical. There is a small angle between them, and that causes this. So some of these things we know very well by now, and many of these are from earthbound observations. But in the late 1950s, people started thinking of actually going to the moon. Okay.
Interesting.
And that was actually a very big leap of science, a very big leap of technology. And we are used to seeing pictures like this, the one that I am showing you for the insides of the moon. Now you might wonder how we know about the inside of the moon when we don't even know the inside of the earth properly. But essentially using similar techniques, we have been able to say, or at least judge reasonably, what is there inside the moon. And we also know to a good extent what the chemical composition of the minerals or the surface soil and so on is. And by and large, this information has come about by probes that went to the moon.
So sir, we know about the measurements and the distances of the moon from the earth and so on and so forth. So how did we trace all of this information?
Russia sent a mission to orbit the earth. That was the first space mission, very small mission, but nonetheless that was a big step ahead. And then the space race started actually. The United States and the USSR were in competition to send out different space probes. And in 1958, Russia planned a mission to the moon. Now of course this mission was not a manned mission, it was just a machine mission. And then then America couldn't be far behind, and then the race started. Yes. And within about a year, but not just one mission, there are multiple missions, within about a year Russia managed to drop a first man-made object on the moon. Of course this was just a very small step, and it didn't yield much by way of scientific information. But in the decade after that, culminating with the American Apollo missions, many missions went to the moon. Some of them were missions that had components that landed on the moon, did some surveys. Some of them were just spacecraft that orbited the moon. And finally, of course, when in 1969 Armstrong landed on the moon. And all of these missions, of course there was this the race and so on to get to the moon was there. There was a lot of national pride and fight and the competition. But nonetheless, keeping all these things aside, coming more specifically back to the question that you asked, is that these missions did varieties of surveys of the moon. And these surveys largely instrument based, which landed or which were orbiting, gave us a lot of information about the soil composition, the surface, whether it is smooth, whether there are craters, hills and so on. And one of the things was to search for whether there is an atmosphere, there is oxygen, there is water and so on.
With the 1969 mission of Neil Armstrong, after which even there were Apollo missions like Apollo 17 in 1972, where America had also sent humans to the moon. But there have not been any manned missions after Apollo 17. So why is that so?
This is not a very easy question to answer, because I think it has many non-scientific and non-technological angles to it. I mean, if you ask me personally, I think it was just a race waiting to be finished, and America won the race of sending the human to the moon. But the usefulness of sending humans to the moon was very limited. Okay, because if the main purpose is to get scientific information about the moon, then in the decades that have passed since the first manned mission, our ability to build very sophisticated machines that can sort of do things automatically, or even take decisions and so on based on the data that is collected at that instant, has improved enormously. So the value of sending a person to the moon and getting very limited amount of data, because it's not a place where a human can easily move around, right? So you can't do much by sending humans. So the risks in sending human missions is just huge compared to sending machine-based missions.
Yes.
And I think that is why that race stopped at that point.
Today we have advancement in technology and everything, but what about the early missions? What was it like in the early phase, and why did the early missions fail?
Yeah, so this is actually quite an interesting history. You'd be surprised to know that the first 7 missions to the moon actually failed. And they failed not just not that they didn't take off or anything like that, but they didn't manage to reach the moon.
Okay.
And the reason I think for that is, like you said, the technology of the 50s and the 60s was way sort of less capable than it is today. And it's like, you want to reach a small target which is a great distance away, and unless you have very good control over your craft and you are able to point it correctly, control its speed, and so on and so forth, and also at the same time know where it is. That's also important. So unless that is very precisely known, it's not surprising that some of the early missions failed. It's like asking somebody to throw a stone or hit a target far away and expect that in the very first attempt everything will be right. But yes, certainly things have improved very significantly, and we have much better success rate in reaching the moon in the recent decades. And what I would like to highlight is our own the first Indian mission, Chandrayaan 1, was the very first attempt, and we succeeded in the very first attempt.
So would you like to describe about the America's mission or Russia's mission, and what contribution did they have?
Okay. Yeah, I mean, I'll just tell you very broadly. I don't have, I won't be able to give you all the details in a very short time. But so the manned missions of Apollo, followed by the lander missions and rover missions of Russia, we managed not only to survey different parts of the moon, primarily near the equator, moon's equator, soil sampling, some information about what is there inside the crust using techniques that are very similar to what we use on the Earth, plus the chemical composition of whatever thin atmosphere there is on the moon, and we also brought back samples.
Okay.
So a fair amount of moon rock and moon soil has been brought back by these missions, and then later analyzed in the laboratories on Earth. And actually, and after the 90s, other countries also joined. So I mentioned our Chandrayaan, but in between, the European Space Agency, the Japanese Space Agency, the Chinese Space Agency, all of them have had successful missions to the moon.
Interesting. So, sir, it's all with the spacecrafts that we are launching on the moon, and we need rockets for that. So, I'm interested in understanding how these rockets are launched into the atmosphere, which carry those spacecrafts.
Right. Yeah, that's a very, very fascinating, what shall I say, fascinating technology, fascinating, progress, I would say, that we have made. So the first rockets, if you would like to call them, were actually rockets used in war, in the Second World War. Okay, that is where the whole story starts. But then after the war, these rockets slowly got converted to missiles.
Okay.
I mean, small rockets, then bigger rockets, greater range and so on, but primarily used for weapons.
Okay.
And then in the 50s, as I mentioned earlier, these rockets were then, people saw the use for these rockets for sending things into space. And one of the biggest challenges for these rockets was to put in enough energy, power, whatever you want to call it, to be able to escape the Earth's gravitational pull. Otherwise, they would just fall back. Right? So missiles fall, right? They go up and fall somewhere, but they are meant to fall there. But in a rocket for space missions, what we want is we want it to be so powerful that the thing really doesn't come back. Right? And that makes it a bigger engineering challenge. A space rocket is a bigger engineering challenge, and like any small rocket that you can think of, whether it's a small artillery rocket or an infantry rocket that is used in a war, or an intercontinental ballistic missile, all of them carry some fuel on themselves. Right? It's not like a stone that you throw.
Yes.
A stone doesn't carry its own energy, fuel, nothing. I mean, it cannot propel itself.
Yes.
What you throw it with, that is the force there is, and nothing beyond that. But all of these actually carry some fuel, and that fuel increases its capability to, first of all, have sufficient energy to escape, and also when carefully done, when cleverly done, this fuel can also be used to change the speed or change the velocity of the rocket, so that you can go in a desired direction, which is very important for a space mission.
Yes, interesting.
And I think what I would also add is, unlike these smaller rockets, the terrestrial rockets, let's say, these rockets meant for space are never in one unit, right? They are always multi-stage rockets, as they are called, typically 3. And the reason why this is done is, as I said earlier, you need enormous amounts of energy to escape the Earth's gravity. And if you want to send a large satellite for whatever observations you want to make, then the task becomes even more difficult. So the rocket has to carry its own fuel, so to speak.
Yes.
Vast quantities of fuel, nothing that we can even start imagining. And then, the very, very crudely speaking, this fuel has to be stored in a container and burnt using appropriate techniques. So, there is either a burner or an engine or something like that. So, there is a lot of mass there, and mass is an enemy for a rocket. The lighter the rocket, the better it will travel, but you have to carry fuel, so that adds mass.
Yes.
So, it's a never winning battle. Okay. But then what you can do is, once some fuel is consumed, you drop off the part which contained the fuel and the engine that was burning that fuel. Okay,
So
that's a trick. So makes it lighter. So the second stage is lighter than the first stage, but by then you have already gained a lot of speed. Repeat the same thing after the second stage. Repeat the same thing after the third stage. So by doing that, you will reach speeds which you could not have achieved by just firing it once.
Wow.
And that's really the trick behind all space rockets, that they are multi-stage. They have fuel in different forms, and like you see in this picture, the fuel is in, or rather, it's a 3-stage rocket shown in 3 different colors, and they will all fall off one after the other. And then finally, this is something I think a lot of people don't appreciate, is that the useful part in a space mission, useful, when I say useful, I mean the actual spacecraft that is going to do the observations, that sits only in this very small top part of the cone. And typically, it will probably weigh something like, I don't know, maybe 1% or 2% of the entire mass of the rocket, a very small fraction. The rest of it is all either fuel or parts that are going to be just dropped off.
So which means you're reducing the weight, and that's how you're accelerating the rocket.
And this just, the interesting thing is that all of this, the basic mechanics, the basic equations, can all be traced to Newton. So in these 300-400 years, very little has changed as to what kind of conceptual framework is needed for sending a rocket. The technology, of course, is very modern, but the basic physics ideas date back to.
Wow, interesting. Talking about the rocket and the spacecraft that it contains, we see that in case of rocket launches, when there are poor weather conditions, usually this rocket launch gets delayed. So why is that in case of poor weather conditions, we do not launch rockets?
Right. So this might seem, like a very, very strange thing to do, because you have such a powerful rocket. What is a little bit of rain or a little bit of wind going to matter? So in a way, yeah, I mean, you are right that it shouldn't matter. But the thing is that, rocket launches are not like trains or airplanes that are, leaving one place every hour and reaching another place in the next hour. They don't happen so frequently. They are far more complex. So first of all, you want to take as little risk as possible.
Okay.
So that is one part. And there are some real risks. I mean, I'm not underplaying the risks. The thing is that rockets have a lot of sensitive electronics.
Okay.
The controls and so on are very sensitive, and that needs to be protected.
Okay.
And it also, as I was just saying, it contains unimaginably large amounts of fuel. So if anything goes wrong in the electrical circuitry, and especially when there is rain and the rocket is wet and so on, there is always this risk of short circuit and things like that. I mean, not very easily, it doesn't happen very easily, but that risk is there. And you have a hugely expensive object sitting there. Why take the risk? And then the risk of a short circuit for a rocket just spells doom. It will just burn off in no time. Yes. Well, 90% of what is standing there is fuel, an extremely rich fuel. So that's a huge risk.
Where the spacecraft is sitting on the top of the rocket, and we have booster rockets which are attached to the sides, to the bottom sides of the rocket. So in case when the spacecraft enters the almost outer space, escaping the Earth's atmosphere, so these booster rockets get separated, and the main spacecraft is the one which heads its journey forward. So what happens to these booster rockets after they get separated?
Right.
And
yes. So I think what I'll do is, I'll just to put your question in context, let us refer to the Chandrayaan 3 rocket. Okay. So instead of talking just in terms of some imaginary rocket, let us focus on the Chandrayaan rocket. And Chandrayaan 3 rocket, I'm sure you have also seen the launch.
Yes.
And you don't see it falling, the question that you're asking, you don't see it falling, but the commentary says, solid rocket, solid motor separation or something like that, right? Yes. So that is when the first stage of the rocket, as I was telling you, it sheds its own weight. So Chandrayaan 3, if you look at, the Chandrayaan 3 rocket is again a 3-stage rocket, L4M, what is it called?
LPM.
Yeah, sir, correct. So this Mark 4 rocket, and it has 3 stages. And the bottom stage, the lowermost stage, is a solid propellant. Okay. So it is some solid fuel which burns and gives the initial lift, and that falls off, and it falls off in a very short time. So you'll be surprised to see. I mean, let's again look at specifically at the Chandrayaan figures, and so before we go to how it falls, let us just for the sake of getting some idea of how big this enterprise is. The Chandrayaan 3 rocket is about 40 odd meters tall.
Okay.
Right, so which is like a 11-12 storied building. Yes. It's that tall, and it has its weight at takeoff, including all the fuel, is some 600 and odd tons, 640 something tons. And the spacecraft that it is carrying is a mere 3.5 tons. Okay. So roughly, I mean, it's less than 1%.
Yes,
right?
absolutely.
About 0.5% of the weight of the rocket is the spacecraft. The rest is all fuel and the engines and so on. So this first stage will fall off, and it falls off in a very short time after takeoff.
Okay.
So if you look at this, I mean, this is the data you can very easily find on the ISRO website. Very fascinating numbers. You'll see that in this chart, you'll see L110 ignition, which is the liquid stage ignition, right, which is the second stage. The first stage is the one that takes it off from the ground, and at 127 seconds from takeoff, which is just a little over 2 minutes, the first stage separates off. Okay. Now at that point, or that time, the rocket is about 62 meters, 62, sorry, not meters, kilometers up in the sky.
Greater height.
Yes, it's a great height. But if you remember, or if you know where the rocket launch took place, it is on the coast.
Yes.
And the rocket takes off in a slightly eastward direction, so that whatever is going to fall off, it just falls under gravity. After the stage is burnt off, after all the fuel is burnt off, it will just separate out, and there's some mechanism to release it, and it falls under gravity, and it falls somewhere in the ocean.
Okay.
And you might have even heard some news about something getting washed up on the Australian coast or something like that. It was later found to be part of Chandrayaan 3. So these things fall off and just fall to this ocean. But then the second stage, where you have the liquid engines, so those don't fall off, they just burn off. Because when they start falling, They have to cut through the Earth's atmosphere, quite a lot of.
So they get burned by the Earth's atmosphere itself.
The third stage again the same thing happens, because once it starts falling, it generates a huge amount of heat and it burns off.
So now we have reached a stage where the spacecraft is into outer space, and we have some parts of the rocket carrying it, say, just to move it forward. So in that case, now we know that it is into the outer space and there is no atmosphere in the outer space. So how does the fuel in the rocket keep burning, and what helps the rocket to carry on this combustion?
So, the fuel that is there in the rocket burns on its own, so to speak, in the sense that the oxygen is provided as part of the fuel itself.
Okay.
Because it doesn't depend on the oxygen in the air to burn. The amount of oxygen that is available in the air for burning, for producing such a lot of energy and at such a high rate, is just not sufficient oxygen.
Okay.
So most of the oxygen is provided via the way the fuel is designed.
Wow.
So the liquid oxygen and liquid hydrogen,
Yeah.
okay, that combination
They
combine and give you
So you don't need
thrust.
any external.
Right, but of course, what I told you for the hydrogen oxygen, that is for the third stage, where it's a cryo engine. But even for the liquid engine stage or liquid fuel stage, you have on board. I mean, the chemical composition is such that, like a firecracker,
Okay.
the firecracker burns not because of atmospheric.
Yeah.
Not really because of the atmospheric oxygen. The chemicals in the firecracker provide the oxygen required for burning. It's very similar.
Yeah, so now we would further carry on to the spacecraft's journey towards the moon. So even before the spacecraft heads towards the moon, it has to somehow escape the Earth's gravity. And for that, what kind of say strategy do we use?
Yeah, so see, I think a very simple, very straightforward strategy is to put in as much fuel as is required and just take off in a straight line, or whatever small curvature that there will be because of Earth's rotation and so on, but essentially go off on a straight long path. And that is a method that is used by for some purposes, and in particular for the manned missions. This is what was used. So you take off pretty much in a straight line.
Yes.
Towards the moon or whatever, but that requires a huge amount of fuel and a much larger rocket. So for example, the Saturn V rocket, which took the Apollo 11 astronauts to the moon, even to date it is the biggest rocket built.
Okay.
And by a good margin.
Okay.
Okay. And if you compare it with our Chandrayaan, I think it's about 10, well, it's not 10, it's about 6 times larger.
Okay.
Okay, in terms of mass. So you just need to build a very big rocket and go straight. But there are other strategies, like what Chandrayaan 3 is using, which is that you go up in a sufficiently high orbit. So which, if you look at the numbers on ISRO's website, you will find that it will typically go to a few hundred kilometers height, and by this time your rocket is gone. Now what you have is only the spacecraft. The rocket is only Chandrayaan 3. That's all, right? And the rest of the rocket has burnt off, fallen, and the end of the rocket. Now the spacecraft is going, and this spacecraft now has to go in the right proper direction. That is extremely important, because it's easy to lose a spacecraft.
Yes.
Slight error in the trajectory means it will be gone. But now the spacecraft itself has some fuel on board.
Okay.
And small rocket-like things which are called thrusters. I mean, they are not really rockets because you don't lose them. They are always part of the spacecraft. And these thrusters essentially do a job similar to the rockets. But it's just that the amount of thrust or amount of fuel that they can handle is very small. It's primarily meant for making small corrections to the direction and change the path, change the trajectory of the craft. And what has been done for Chandrayaan 3 is that you go up in an orbit which is about 150 kilometers or so, thereabouts, or maybe a little larger, 200 kilometers, and then you start making a very long, sort of not a circular but a very elongated circle, which is called an ellipse.
Okay.
So an elliptical path around the moon, around the earth first, and this ellipse becomes larger and larger after a few stages. So you might have, if you had seen the chronology, then on certain dates there were these orbit raising maneuvers.
Oh.
So essentially it's just this: you have a small orbit, you give a command from the ground station and fire some rockets so that it changes its path a little bit, and that little bit will take it on an even larger orbit.
Okay.
So this has to be timed extremely precisely, and a very precise amount of thrust has to be given. If you do that, then the orbit keeps on growing, and ultimately the orbit is so long. It is still bound to the earth, by the way,
Yes.
because it's going around the earth, but it is so long that its longer side, or the length of that orbit, is very close to the actual Earth-Sun distance, Earth-Moon distance, very close to that.
Okay.
And then you give it a slight kick so that it then escapes from that earthbound orbit, enters into what is called the translunar orbit, and starts moving towards the moon. Okay?
Yeah.
And now you do the reverse. It is near the moon, and you slowly circle it and keep going in ever smaller orbits.
So,
And
sir,
that's how the trajectory.
so in that case, when the spacecraft is in its outermost orbit of the Earth, like let's say it's on the outermost gravitational orbit, and we are in a sure shot that within this deboosting or within this maneuver, we are going to just eject it into the moon's orbit. So how do we ensure at that particular point it does not escape anywhere into outer space?
Yeah. So see, that is a very tricky maneuver, and that is one thing that I think all aerospace engineers dread this dread this instant, because if something goes wrong, there is almost nothing you can do to correct it.
Okay.
Because it is hurtling at a great speed, I think about 10 kilometers per second or so, and by the time you make some corrections, it has already gone several kilometers away from where it was supposed to be. And I mean, even more important than the distance is the direction. If the direction is wrong, if the distance is wrong, maybe you can still do something about it. But if the direction is wrong, then it's very hard to make a large correction and bring it back. So it's pretty much a question of getting it right the first time. You can't change much. But getting it right the first time doesn't happen by itself. You need to plan a lot and control a lot of things.
So, sir, when Chandrayaan 3 has been so much far from the Earth, at a very far distance, so how does it communicate with the space stations on Earth? So, does it have any intrinsic sensors, or what is the navigation of Chandrayaan 3?
Correct. So, all spacecraft, okay, irrespective whether it is Chandrayaan 3 or any other spacecraft, all of them have multiple modules or instruments to ensure that they stay on course and to ensure that they can communicate back with the Earth. So, these thrusters and sensors together form the navigation modules, and it's like if somebody asks you for an address, you tell that person, okay, you go down this road and you will see a tall red building and then a shopping mall on this side, and then you will cross a bridge. So, these are kind of landmarks that you follow in order to get to your destination. And for the Chandrayaan or any other spacecraft, it's not very different. Of course, it's far more complicated, but the idea is the same. That you look at certain fixed points in the sky or in the outer sky and look for stars whose positions we know don't change much with time.
Okay.
And you identify these stars, and relative to that, you look at what directions these stars have relative to your current position. Okay. And then by what is called triangulation or some equivalent of that, you can find your own position, so to speak. relative to these stars, and then you also know relative to that point where the moon is. So you know, okay, now I need to go slightly to the right or left or whatever it is. And that's how this happens. And for this, there are onboard star sensors, and there are also these what are called inertial navigation systems, which don't depend on external references, and both together allow you to do this.
Interesting. So, with the help of Chandrayaan 3, what is it that India is tending to achieve? Like, so now our objective is the south landing on the moon, but what else do we tend to achieve through Chandrayaan 3?
Yeah. So, see, if you recall this whole Chandrayaan series of missions, there are two goals, broadly speaking. One is a technology demonstration goal, which means that we as a nation try to show that we are capable of doing some technologically very demanding stuff, and also enhance the technological capabilities of our community by and large, because a lot of people contribute to this. Yes. Although it might seem like just a handful of people at the control center doing things, but that's, everybody knows that a lot of people work behind the scenes, and not just people within the space community, space science community or ISRO and so on, but even even the industry that contributes to this technology. So it's a confidence boosting thing for the nation, and there are also some scientific objectives. Okay. Right, and in fact the major part of what Chandrayaan 3 is planning to do after the landing is a scientific mission. So it will it has several instruments on board, and it will try to get the chemical composition of the soil, try to look for say water or other minerals, and also observe the Earth from the moon. Okay, that's another one of the objectives, and the reason why this is being done is to get a sense of what somebody far away might think about the Earth. Yeah. If they were to get an image of the Earth, what is it that they would?
That is something which we were dreaming of.
Right.
Like
so it's correct. So that's another thing that is being planned, and once these things land, they'll do the surveying and send the data to the ground stations, right? And let me just add one very something that not something that is not very easily recognized or doesn't strike most people, is that we think that we are, it's India's mission and so on, but these things don't happen without the cooperation of other countries.
Yes.
So it's sure, most of the things have been, it's certainly our mission, but once this craft leaves the Earth, it is going around the Earth first and then going towards the moon, and also going around the moon for some time. So for a large part of its journey, it is not going to be visible from Bangalore or Sriharikota or wherever our space stations are. Right? Yes. Because maybe it's at the back of the Earth. Yeah. Back of the Earth meaning the other, that's what I mean, or the back of the moon or whatever. Okay, and we are not going to be able to see it. So in such situations, if you lose contact, or if you can't communicate or do any maneuver and so on, it's likely that the spacecraft will be lost because you have no contact, no control. Absolutely. Right? So the timing of all these maneuvers is extremely critical, and cooperation from other countries where they will download some of the data and pass on to us, or they will send a message on our behalf. This kind of cooperation is extremely important, and especially for our Chandrayaan 3 mission, when this finally reaches the moon, we are not the only country that are going to be in contact with them. Yes. It will be a network of things so that the communication and information flows properly.
So, sir, with Chandrayaan 3, what we are also interested in knowing is what modifications does it have and what are the instruments it contains so that we can achieve all of this, like the scientific experiments.
Correct. Yeah. So I think what I'll do is I'll first tell you what the Chandrayaan 3 craft is carrying. Okay. And then go down to saying what instruments there are. Okay. So I think most people by now know that there's an orbiter, there's a lander, and there's a rover. I think everybody knows this by now. It is such an important thing for us, and it is constantly being talked about. So all of us know this. So the orbiter plus the rover plus the lander plus its fuel, don't forget the fuel, it's needed all the time, and its navigation, etc. All of that forms the Chandrayaan 3 spacecraft. So this Chandrayaan 3 spacecraft, now talking in terms of the instruments, has three sets of instruments. One instrument will stay with the orbiter, the part that will keep going around the moon, even later on. Then the other half is going to land, which is the biggest part of the spacecraft. That is going to land on the moon, and this is going to happen very soon, and we are all looking forward to it. Once this lands, the very very large rover plus lander part with its fuel, once it touches down, a small cart kind of thing will slide out of the lander, go to the soil and do a soil survey. That is the rover. The rover is really the small kid on the block, and the lander is a bigger one. And then this lander carries bulk of the instruments, and the instruments that the lander carries are there for doing different surveys. And one of the things is it will try and do some subsurface measurements, so seismic kind of measurements, soil measurements, and of course there are multiple cameras. They'll keep sending us images, but we'll also be looking for specific minerals by using it's basically a chemical composition analyzer and an instrument. And now this on the small, this rover that is going to go around, there are again two instruments to essentially study the soil, the composition of the soil.
So, sir, in case of Vikram lander for Chandrayaan 2, so the only part with Chandrayaan 2 was that we missed the Vikram lander by a few mistakes. So what modifications does Chandrayaan 3 have to ensure that we have a soft landing?
Right. Yeah, so I think this is a question topmost on the minds of everybody who is associated with these space missions, which is that in case of Chandrayaan 2, as you rightly pointed out, we failed in the last part where the Vikram lander crashed rather than soft landed. And it is understood that the reason for it to fail was that its speed could not be controlled properly, the direction also could not be controlled, and it actually toppled and hit the ground way faster than it should have. So essentially what it means is that barring that last phase of, I think, a few kilometers, everything that was planned for the mission went off well, and it's a very complicated planning. So in the new version, Chandrayaan 3 version, there is much more by way of instrumentation to control the landing. Okay, much better planned and much more intricate set of technology and more active technology, so to speak. It will take images, make some decisions in situ and so on, and that will ensure that, we hope that it will ensure that it will land. I think there's some 9 or 11, some very large number of instruments, which are part of the lander, primarily to ensure that we have soft landing.
Yes. So, also, are there any specific reasons that we have targeted South Pole for a landing this time?
So the South Pole of the moon is a very less explored space. most of the early missions have landed close to the equator. I mean moon's equator, lunar equator, and that region has been studied better than the rest. Right.
Okay.
So the South Pole landing, I mean, going to the South Pole is more important because it's less explored, and for various reasons, there is reason to believe that there'll be it's likely to have a richer, might offer us a rich variety of minerals, and possibly also water.
So, sir, Chandrayaan 3 had given us evidence of water. So, how do you think do water molecules exist on the moon, like in what form?
Yeah, so what Chandrayaan 1 has done and what Chandrayaan 2 wanted to do was to explore this water business further. And Chandrayaan 1 gave us evidence that there is frozen water.
Okay.
So, the temperatures on the moon are very extreme. And okay, by the way, because we are talking about these extremes, it is important that the Chandrayaan 3 lander lands close to the South Pole, but on the bright side. Okay,
Yes.
because if it doesn't reach the bright side and instead goes to the dark side, it will not have enough power to power its instruments. It requires the sunlight to power it. Okay, I mean that's important. But anyway, leaving that aside, because of these extremes of temperature on the moon, the water that has been observed is estimated to be in the frozen condition, and part of the soil, not like it's not like flowing water. So ice in some form, but also not ice as in you won't find I mean, I don't know, but what I'm just trying to point out is that it's not like a block of ice will be available, will be found. It will be water dispersed in the soil, but in a frozen form.
So, with all of this, as we are sending spacecrafts on the moon and also we are exploring the space, there is also an ever increasing amount of space debris that is created in the outer space. So, are there any plans to manage this?
So, see, the thing is, you're right. I mean, this problem is an ever-growing problem. But okay, since we are talking of Chandrayaan 2 and since you asked about debris, let me point out something, that the Vikram lander and the Pragyan rover from the Chandrayaan 2 mission has crashed on the moon, and there is photographic evidence for where it is and so on. So that's certainly debris on the moon. But the Chandrayaan 2 orbiter is still going.
Yes.
And the Chandrayaan 2 orbiter is actually going to be part of the Chandrayaan 3 mission.
Okay.
And how? Because once the rover lands, once the lander lands, it is going to communicate with the Chandrayaan 2 orbiter, and that will be used as a relay station for the signals, because the Chandrayaan 3 orbiter has a different orbit purpose and so on. So having two sort of relay points, so Chandrayaan 2 is going to be used. But yes, you are right that the space debris is an increasing problem. On the moon, there are already several missions which have reached and they have left their debris there. And in the open space also, I mean the free space in between, you're right. There are some websites which will show you where different satellites are today, and you'll see that there is a lot of things flying about. So for spacecraft where control has been lost, right, or when they have run out of fuel, depending on which direction they were pointing in when they lost control, they might just escape to great distances and nothing will happen. But there are many that are orbiting.
Yes.
And those pose a fair risk. And sometimes, some craft where you have control, you still have control, and their mission life is over. Sometimes these craft are actually lowered to the Earth's orbit and they burn while descending. So that's one way to remove the debris. But you are right. I mean, it is growing.
So I think Chandrayaan 3 has been an inspiration for millions of us, and also it has proven an advancement in space technology and space science.
Yeah. So see, Chandrayaan 3, when it succeeds, will be a major game changer for us, because the first time we'll be carrying out a proper scientific, observation mission. It will give us data from the parts or the regions of the moon from where there's been very little information coming, and this will certainly propel other nations also to think of such missions if the data that comes out is anything interesting, and it often is. And then also further, one can think of bigger missions and so on to explore the vast number of things that is there on the in the space. And it, as I had pointed out earlier, there is certainly technology boost and so on. And future missions. So, some of you might have heard of our earlier Chandra mission, right? Or even the Astrosat, which are like scientific observation missions based on satellites which are orbiting the Earth. But the reason why we go to these higher orbits is because not everything can be seen from the Earth. Yes. Like right at the beginning, we had talked about how one half of the moon is not visible to us. Similarly, there are different parts of the cosmos that we can't see from the Earth, or if we can see, then there are limitations. So, some satellites orbiting the Earth and carrying the same instrument that we would otherwise have placed on ground are what are called scientific satellites, and we have several of them. There's and then you get much more information about astronomy. I mean astronomical cosmological information about this, and our next nearest neighbor, so to speak, beyond the moon, depending on which direction you go in and which time of the year you are looking at and so on, could be either Mars or Venus or whatever. So there are plans for missions. We already have a Mangalyaan mission. It is only an orbiting mission, but NASA already has a rover on Mars, and there are plans to go to Venus. And there's also an upcoming mission of which I am part, which is the Aditya L1 mission, which is again a scientific mission to observe the sun. So this is a mission that we are hoping will be launched. The spacecraft will be launched in a month's time or thereabouts. And this is a mission to observe the sun. It will go towards the sun. It will not go very close to the sun, but go in the direction of the sun and keep staring at the sun for a very long time and get.
Yeah. So thank you so much, sir, for your time, and we wish you success for Aditya L1 and your future endeavors. Thank you, sir.